Hi and welcome back. So in the last video we imported an animated mesh of seagulls, of a seagull, made it loop, and then we made some particles and got those particles to follow an animated sphere. We also used the animated sphere scale to change how far apart the particles try to stay from each other, so that we went from small flock to sort of spread out flock to and then towards the end of the animation they gathered back together a bit more. So one of the other things that you could use in this is like a speed limit. So you might have a pop speed limit to stop the particles getting above a certain size. So if I do top speed limit, and we can wire that in, and let's have a look. So what I'm actually looking at here is the maximum speed. Maybe I'll try a speed of maybe 20. We'll see what that does. Yeah, it doesn't seem to be affecting it too much, but maybe I'll try a 15. Rewind it, play it again. So that's just one of the things that you can use to sort of wrangle your particles to get them to do what you want, sort of control their speed. So we've got the pop attract, so it's following the sphere. Then we've got the pop flock to get them to, we're mostly using that for keeping them from hitting each other, but there are other settings in there. I recommend you checking those out. Don't forget that you can hit the question mark for help on any node in Houdini. And then we just added a speed limit that we might want to play with a little bit more as we're getting things going. So as I mentioned, you're likely to have to play around with at least the force scale and the goal velocity to get your particles to follow your goal object nicely. Also, the maximum speed on the pop speed speed limit value will help you get things under control as well. So if you inside the pop now, if you hit tab and type pop, you can see that there's a lot of particle operators that you can use. I recommend experimenting with as many as you can, and don't forget, as I just said, that you can get help on any of these by hitting the question mark up the top right hand corner of the properties panel. Okay, so we have some particle animation. Let's put the seagull meshes back on by activating, going out of here and activating the copy stamp. Okay, so if I zoom in, let's have a look what's going on here. I'll stop the animation and I'll zoom in. So you can probably see that they're all sort of facing in sort of random directions. So to fix this, we'll need to modify the point normals on the particles as they come out of the pop net. So we need to fix the normals here based on the velocity. So they have an initial normal that we assigned up here, I think, yeah. Sorry, we assigned the normal up here and then we converted that to velocity. So we need to convert one as they're coming out of here. So we need to make a normal from a velocity. We're doing sort of the opposite of what we did. We made a velocity from a normal here, but then we're going to use the velocity out of here and turn it back into a normal to be able to point the birds in the direction that they're flying. So after the pop net, add a point wrangle, or an attribute wrangle that we're going to be going over points. Make sure that that's points. And we're going to say at capital N equals at small v, and then semicolon. Okay, let's see what that's done. Alright, so that seems like they're all sort of heading in the direction that they're flying, which is really cool. So next, to make sure that they're actually facing the right way up, let's add an up vector in the wrangle as well. So we'll just do v at up equals curly bracket. This is a curly bracket, the one that's above the square bracket. and make that 0, 1, 0, close curly bracket, and then semicolon. So that's just to force them to be up, facing up at the moment. So to show what it does, let's change the value to 1, 0, 0. So it'll be pointing the up vector along the X in the world. So let's have a look at that. So you can see that they're all kind of sideways now, pointing along the X in the world. The up node is along the X. So that's not what we want, so I'll just change that back. So one thing that you might want to investigate in your assignment is how to get the birds to tilt or bank as they're turning. At the moment, the way that we're setting this one up, they're just straight up and down. But if you can get them to bank as they're turning, that would be a really good thing for you to do. So the next thing we're going to look at doing is driving the animation, the speed of the cache playback on the birds based on the speed that they're flying. And also we'll try and randomize the start frame, because they all start in the same pose, even though that, you see they're all there with the wings up, and then they all fly off using the exact same cycle over and over and over again. So I'm going to add a time shift over here after the time warp. So the time warp is what we use to get it to cycle, but what we're going to do is add a time shift. So what this is doing, let's activate that and just shift G to zoom into where it is. And at the moment, the animation is actually being driven by whatever frame it's on. So 46 drives 46. So I want to disconnect that or delete the channel, so we can see that if we move it by ones, we can actually just make the animation run. Okay, so what if we could have a value on each particle that adds up how far that particle has traveled on each frame, and then use that value to drive the animation of the gull that is copied to the particle when it gets copied down here. So that's exactly what we're going to do now. In the same wrangle where we copied the velocity to the point normal and added an up vector, which is the one over here, type this: at anim frame equals at length bracket at v close bracket semicolon. Okay, that's basically setting per point. We're going to set an attribute called anim frame that is the length of the velocity vector. So it's basically how far has the particle traveled since the last frame. That's exactly what we're doing. So to calculate how far each particle has traveled this frame by getting the length of the velocity vector, and it will store that value in a point attribute called anim frame. So after the wrangle, add a solver. A solver is basically solver. Actually, let's see what the attribute wrangle is complaining about. At anim frame equals. Sorry, not at length. So at anim frame equals length of the so velocity vector there. Yep. So a solver is basically something that can do a calculation on a frame, and you can use it to add to whatever the value was on the last frame. Basically, we're going to use it to accumulate the distance that each particle travels on each frame and store that in the anim frame attribute. The solver is extremely useful and can be used for many things. I describe it as a history-dependent memory cache. Okay, so dive inside the solver and make an attribute wrangle. So make a wrangle, make sure it's on points. Wire input one of the input one into the first input of the wrangle, and then previous frame into the second the input 2 of the wrangle. So make sure the wrangle is set to points, yep, as it is, and type this in the expression window. So at anim frame plus equals at opinput, so optional input, op input 1 underscore anim frame semicolon. It's important that you type that correctly. So at anim capital Frame plus equals at opinput1 underscore anim capital Frame. So what this is doing is taking the current length of the velocity on this frame that we just created with the wrangle here. It's going to take that value and add it to the previous total. So it's making a cumulative value of how far each point had traveled in its life. So it's important to make sure the wrangle is set to be displayed in here. I forgot to do this earlier and it took me ages to figure out what I had done wrong. So in the copy stamp node, go back out and go to the copy stamp. We need to make sure that stamp inputs is on. So meaning that it's going to transfer attributes from the particles to the gulls, and we also need to tell it what attributes to transfer from the particle to the resulting geometry when it makes the copies of the animated seagulls. So check stamp inputs there, and in the attribute stamps add in the anim frame, so anim capital Frame. So that's the value that we're going to be applying from the particles that's been accumulated through here. Each particle has its own distance value that it's traveled in its lifetime, and it's going to copy those onto each of the meshes as it's copied onto the here when it's duplicated. So stamp inputs, yep, add in anim frame. So the anim frame is going to be used to drive the animation based on how far each gull has traveled. So in the time shift node, that's just before the copy here, this is the one that's going to set the time shift for each copy that's going in here. It's going to be driven by the value that's coming in here, the anim frame. So in the time shift, in the edit text next to the frame, type this. Okay, stamp brackets inverted commas dot dot copy to particles inverted commas comma anim frame comma 0 close brackets. Okay, so what you might want to do is double check that the copy to particles name here matches exactly that, and also the anim frame attribute that you've been working in here also matches this anim frame here. So let's activate the copy to particles, or the copy stamp, and see what's happening. Zoom out. Alright. Okay, the animation looks like it's been driven by the velocity, length of the particle's motion, but all the birds are starting at the same frame of the animation. So if we go back to frame 1, they're all starting still with the same pose. So what we could do is use the ID of the particle to change the frame that each one is offset by. So what we need to do is utilize the ID. So to stamp each copy of the gull with the particle ID that it's copied to, we go back to the copy stamp, and after anim frame type in ID. So so next we need to add that into the time shift of each of those. So to access the values that are down here, we're going to copy this because it's the same syntax, and we'll just do a plus and then we'll paste it in afterwards. And instead of using anim frame here, we just change this one from anim frame to ID. So now what should happen is the ID of each particle, going from 0 through to 99, because there's 100 particles, will get added to the animation that we're doing for each gull. So that should, there we go, basically have an offset starting point, and so the animation is actually being driven by the motion of the gulls, by the motion of the particles, and it also has a random offset that we're utilizing so that it doesn't look too uniform. So hopefully they'll come back around. So for this, you probably want to cache out the animation because the copy stamp can get a little slow. So you probably want to cache. Let's turn that off wireframe so we can get some nice silhouettes. So what you could also do as well is to randomize things a little bit more. We could randomize the scale because they're all exactly the same scale as each other at the moment. So we could make a up here we could put at P scale equals 1, 1, 1. So this is basically to add the P scale value. Oh, not 10. 1, 1, 1. And then what you could do out here is possibly randomize. Attribute randomize. So you could do that, and then you could set values in here for the P scale, and then you could tell it that no, that's a different one. But you could definitely figure out how to add in the scale in there as well. But I'll leave that for you to figure out, and I'll attribute randomize, delete that in there. So other things that you could use this for are like schools of fish to school underneath the water, or another thing that you could use. I did this a few years ago when I was doing some other stuff in. Oh, it's not actually working. Okay, let me reload that. So this is one that I did in a different piece of software, and I actually wrote a tool to be able to run this. So I was using particles to do the animation along the ground, but then to drive the particles, to drive the meshes, I wrote my own tool. But Houdini's so cool that you can do it directly inside Houdini without having to write tools. And this was just a fun little job thing that I was working on. Okay, so that's pretty much it for this tutorial. So yeah, if you're up for a challenge, you could figure out how to get particles to stick on the ground and have something crawl along at the exact right speed to run the animation so it looks like it's pretty much sticking to the ground. And thank you.